Here I'd like to introduce Gordon Woodcock, past president of the L5 Society. He's written a book on space stations and platforms. He's currently employed at Boeing Huntsville for the Manned Space Advanced Concepts. Today he will be talking on the vertical versus horizontal takeoff of the SSTO. Mr. Woodcock.
Thank you. Let's see if I can find my notes here. I'd like to begin by saying a couple of things that this talk will not be. First of all, it is not a report on the current study activities of the RL-18, the McDonnell Douglas Boeing team, or any of the others. I'm not a regular member of the team, and I don't feel like I'm really qualified to report on team activity. The other thing that will not happen in this talk is that no one is going to walk up to me towards the end of the talk with a sealed envelope in which I open it and say, and the answer is. So I'm not going to say at any point in this talk that the answer is this or the answer is that. I am going to spend a little bit of time in talking about some history and talk about the things that make this a fairly difficult trade to actually resolve. I don't really want to quite start with talking about the picture, but I'll leave it up. In fact, this question of how to take off a reusable rocket has been around for a long time. You can trace it back to a time at which I was about 9 years old, and I've been around for a while, because you can trace it all the way back to the German activities in the Second World War. In 1942, which is over 50 years ago, a German rocket scientist by the name of Sanger developed a design concept for a horizontal takeoff, horizontal landing rocket bomber. It was never built. As far as I know, no one even did any wind tunnel testing or anything like that, but it was a concept. It took off from a sled. It was intended to fly either halfway around the Earth or one way around the Earth. It had wings. It had actually a diesel fuel and liquid oxygen engine. Interestingly, Sanger had in mind to operate this engine at almost exactly the same chamber pressure as the SSME today, 200 atmospheres. At the same time, of course, and much better known, were the activities of Werner von Braun and his associates who built the V2 rocket, and also were doing design work on a larger two-stage rocket, of which the second stage had wings, and the idea was to be able to reach New York City. And the von Braun design was vertical takeoff, and although since it was a weapon, the landing mode was less clear, you could say it was vertical landing. The von Braun rockets that were in the Across the Space Frontier books about 10 years after that, in 1952, 1953, actually used both. He proposed a three-stage rocket, of which the first two stages used parachute recovery and sea landing, which was vertical landing, and the third stage had wings and was a runway lander at an airfield. Von Braun, during the same period of time, also proposed some vehicles to go to Mars, and his Mars landers actually had wings and were intended to be horizontal landers, although in those days people thought Mars had a lot more atmosphere than it really does, and a lot fewer rocks on the ground than it apparently does. A horizontal lander for Mars probably would have not worked. If you step forward another 10 years to about 1962, there were studies of putting wings on the Saturn V, both the first stage and the second stage, with the idea of being able to fly these stages back to a landing site somewhere and land them. And at that time, the thought was horizontal landing. There was also a study of a parachute sea recovery vertical lander for the S1C stage. During that same period of time, from about 1960 1961 or 2 to about 1970, there were a whole host of studies of advanced space concepts, from lunar bases, space stations, missions to Mars, and all that. And a part of that was very big launch vehicles for the Mars mission. There were a couple of studies of big launchers that could put 1 million pounds in orbit in one flight. These were given the names Nova and Post-Nova. No real work was done on these vehicles, but it did get so far as to begin an engine program for the upper stage of this Nova vehicle. There was a hydrogen engine back in the 1960s that was in technology development with 1 million pounds of thrust. It was called the M1, and Aerojet was doing. Now these big 1 million pounders were vertical landers. Generally the idea was sea landing. A little bit, and I probably ought to at the same time mention that there were, during this period of time, in the 1960s through 1970, there was a whole series of studies that eventually evolved into the space shuttle. Initially, they were designed as somewhat smaller than space shuttle, usually two-stage, fully reusable. We had horizontal takeoff, horizontal landing, vertical takeoff, vertical landing. The whole business was in there one way and another. And these concepts, which were designed at that time strictly for space station resupply and exchange, eventually evolved into the shuttle that's now flying, which also, by the way, uses both horizontal and vertical landing. The orbiter lands horizontally on the runway, and the solid rockets land vertically in the ocean with parachutes. The earliest thing I have a picture of is the thing we did at Boeing back around 1972, which now we've moved up another 10 years, so we're now 30 years from the very earliest concepts in 42. And this was a thing that's often gone by the name of the Big Onion. Its intent was to place payloads in orbit for the construction of solar power satellites. It was a single stage orbit. It had both kerosene and hydrogen engines. It had a huge hydrogen tank, a LOX tank, and the kerosene tanks were some of the little ones at the bottom. It took off vertically and landed vertically in the water. One of the reasons that these huge rockets have this short, fat shape is that you have to be very big in diameter to get enough engines in the tail to get it off the ground. So when you go to these 1 million pound payload class vehicles, if you look at this one or you look at the others that came along at about the same time or earlier, they always tended to be relatively short and fat. The Big Onion, as we called it, was intended to land in the water. We really didn't want to land it in seawater, so we had this notion of constructing an artificial landing pond, which would be freshwater at KSC. Let's see what else I have here. This is an artist's concept of a landing pond near one of the. You can see the VAB over there in the left. And it was intended to basically be towed into a dry dock, floating on its rear, and then the water would be pumped out and you set it on a launch stand and prepare it for the next flight. A little later on, we modified that scheme. We made it 2 stages. We discovered that with 2 stages we could get a little smaller vehicle and the same payload in orbit, and we thought it improved the cost performance a little bit. And we also looked at a wing version of it, but I don't have the wing picture. This illustrates kind of the destination for this thing, which was a big construction facility in low Earth orbit. Later on, the SPS concepts changed quite a bit, but I always liked this picture. And one reason that I liked it was that I watched Jack Olson paint most of it, and it took him about 8 weeks to do it because of all that truss work. And the detailing of all that truss work took a long, long time. This was before the days of computers when you could do it by replicating something on a computer screen.
tougher to build the trusses.
Pardon?
It would have been even tougher to really build the trusses.
Actually, they're pretty easy to build.
Okay.
Because it's a very simple repetitive process that you can do with a robotic machine. There have been a lot of other concepts. I'm just going to show some pictures without much comment. These are some trans-atmospheric vehicle concepts. There's a sled launch, an air launch, and a supersonic air launch. This was another scheme that Boeing put together in, I suppose, about 1980. The orbital vehicle was the little detail thing on top. It had an expendable tank and was launched from a 747. It was a single stage to orbit, but with a drop tank. The tank went to orbit, but it did not return. This shows that same vehicle taking off. I've got the picture backwards. Not that it matters, but if you want to read the Air Force on the side, this is correct. The idea was to start two engines for separation, and then once you got separated, you started the others. It was powered by a string of RL-10s. A little bit later, this is another trans-atmospheric vehicle concept, small payload bay intended to go to orbit, supersonic air breathing booster. The final picture was one that was called RASV. This was a horizontal takeoff, horizontal landing vehicle that used a ground accelerator, that's a sled for takeoff. So that kind of covers it for the pictures and the history. If we could have the lights now, turn the view machine off. But the controversy continues. Today we find that there are both vertical and horizontal takeoff schemes for single stage to orbit. There is Kistler Aerospace is a privately funded activity which has a concept for vertical takeoff, vertical landing. It is actually staged. It's not a true single stage to orbit because they have sort of a flying launch pad that takes the vehicle up to altitude. So you can see this is not an issue that's come up in the last couple of years. It's been around for a long time, and there are people who have been for a long time on both sides of the fence. In fact, there's probably a relatively simple observation that one can make is that airplane people tend to like things that take off and land with wings, and rocket people tend to like things that take off and land with rocket engines. And you run into some rocket people that say, gosh, I don't want to have to start engines to land the thing. But the general trend is that the airplane people like things with wings, and the rocket people like things that take off with engines. The recent interest in the vertical takeoff and vertical lander scheme actually goes back to a concept that was developed by a space activist by the name of Gary Hudson. He called it Phoenix, and it first came up 6 or 7 years ago. And that concept subsequently got adopted by Max Hunter, who put a little bit more engineering into it, and advocated the notion that a vertical takeoff machine can land anywhere, which is almost true, unless it's designed for it. You can't really land in the ocean, you can't really land in rough terrain. And if you land in soft terrain, there's some question about what happens, but the DCX proved that you can kind of land anywhere, at least out in the desert. The original Phoenix and the original Max Hunter scheme were things that took off vertically and landed tail first, or entered tail first like a big onion, and then landed. When the BMDO became interested in the concept, they wanted cross range, and these rear end entry vehicles have very little cross range capability. They'll land right on the orbit track with just a little bit to either side. And that brought forth the concept on the part of McDonnell Douglas for a vertical lander, which actually is a conical shape. It enters nose first, and in at hypersonic speeds, a slender cone can generate almost as much lift-to-drag ratio as a winged vehicle. Not as much, but close. And you can get enough lift-to-drag ratio to get the cross range that BMDO wanted. So that kind of led to the current DCX concept. Max Hunter was, and he's here at the conference, by the way. I don't know if he's still here, but I saw him the last couple of days. He was really sold on the idea that you can take this thing off, and if you have an emergency, you can land it on engines at almost any time. And the DCX did that, in fact, on flight number 5. If you think about things that are really intended to go to orbit, it's not quite that simple. When you fly to orbit with a single stage to orbit, your takeoff weight has to be about 90% propellant and about 10% inert weight. And so you have to strain pretty hard to make sure that you do everything you can to minimize inert weight. One of the things that would be done for either a vertical or horizontal takeoff machine is that the vehicle is not capable of being supported full of propellant on its landing gear. So if you do take off and have an emergency, one of the things you'll have to do is burn off propellant before you can land it. You know, if you've been on an airplane that had an engine failure right after takeoff, very commonly the same thing happens, at least if you take off heavy for like an international flight. You fly around for an hour or so and dump propellant before you land. I'd like to spend a few minutes now talking about the comparison between the two. And I'm going to break it down into kind of how does this subsystem respond, how does that subsystem respond, and so on. First on performance, it's nearly a dead heat. If you compare the payload capability of the two, they come pretty close. To first order, without going into any details, the difference between the two is that one of them has wings to land, and the other one carries propellant to land, so that you can restart the engines and slow down for a soft landing. And if you do a first order comparison, it turns out wing weight and propellant weight are about equal. They're both about 10% of the landing weight. So the first order comparison, they're about equal. The vertical lander, at least in the version that has a nose first reentry, doesn't tend to scale up quite as well. If you do a tail first reentry, it scales up just fine, as you can see from the earlier pictures of very large vehicles. What's really going to dictate a choice is not the performance difference, which is small. What's really going to dictate the choice are things like design complexity, the operational comparison, safety, reliability, and just the general cost of turnaround operations. And cost and customer acceptance and risk are going to swing the decision. So it's not, it's not one of these simple comparisons that you can look at that says, hey, this one's got twice the payload of that one, and therefore the choice is obvious. It's not obvious. We begin with structures, as we usually do when we march down through the subsystems. With structures is usually first. The vertical lander doesn't need a wing. And so the structure is simpler, because when you do a wing on an airplane or a rocket, the wing and the wing and the tanks and the thrust structure tend to get in the way of one another, and there's some structural complexities there. The vertical lander doesn't need a wing. But the vertical lander does have fins, and it does have some fairly large control surfaces, so that it's not just a clean case of one of them has a wing and the other one doesn't have anything. The other one's got some stuff too, but it's not a wing. Nonetheless, the structure is a little simpler for the vertical lander. The tanks are actually a little bit more complicated. You have to make conical tanks instead of cylindrical tanks. That's a little bit more trouble, but not very much. The landing gear is, as far as I can tell, it's about a push. They both have to have a landing gear. One of the vertical landers sits down vertically on its landing gear. The horizontal lander has wheels and tires and brakes. But the wheels and tires and brakes are not the big swinger in a landing gear. The big swinger in a landing gear is the structure and how the structure ties into the rest of the structure in order to be able to support the vehicle. Propulsion, the horizontal lander is a clear winner. And the reason is that rocket engine run is about 10 times as reliable as rocket engine start. And the horizontal takeoff vehicle, you start all the engines before you take off, make sure they're running, only then you take off, and once they're shut off in orbit, you don't ever have to start them again until the next flight. Also, the vertical lander needs throttling engines in order to land. It needs fairly deep throttling. The horizontal lander could get by without throttling at all. Now, if you do that, if you don't use throttling at all, you probably run into a situation where the maximum Gs before you get to orbit are higher than the 3 Gs that we're used to on the shuttle. If you have several engines, you can shut some off and do kind of a crude throttling that way. So I think both will have throttling, but basically the horizontal machine can get by with what the space shuttle engine presently does, which is down to 65%, and the vertical lander needs deeper throttling. If you look at engine cycles, if you say the cost of running engines is proportional to how many times you start them, and engine people tend to say that, you don't start engines as many times for the horizontal lander. And control, the aerodynamics and control, the comparison is, well, it's not, it tends to favor horizontal, but it's not a clear swinger. These machines are always tail heavy because they've got a bunch of rocket engines in the back, and rocket engines, even though they're the highest thrust to weight machines that we know of, are still pretty heavy. And putting a wing on the back of the thing tends to help the aerodynamic balance. The vertical lander tends to enter pretty unstable. That's not an issue today because we today fly a lot of airplanes that are pretty unstable, particularly, especially fighter planes and things like that. I remember back in, I was a junior engineer, it was back in the, 1950s, I guess. We had Boeing had an airplane, a pilotless airplane, we called it at that time. It was a missile, but it had wings and a tail. It flew like an airplane. It had a rocket for takeoff and ramjets for cruise. It was called the Wolfe. And the first version of that thing had a liquid propellant rocket engine, and it was pretty stable throughout the flight regime. The second version of it had a solid propellant rocket. The solid propellant rocket was near the tail, and the thing was very unstable aerodynamically during rocket-powered ascent. And the aerodynamicists had a tizzy. My God, fly an unstable airplane? You can't do that. Well, we do it all the time today, so it's not really a significant issue. The vertical lander, because it has a little less wing area, doesn't have any wings, but it's still got a pretty substantial body area, tends to penetrate a little deeper into the atmosphere during re-entry, and it tends to get a little hotter. I want to talk about aero heating, but first I'm going to say, as far as avionics are concerned, they really don't care. It doesn't matter. As far as orbital operations, that doesn't matter either. Aero heating, the vertical lander is a little bit hotter, but it has less area to protect. So which one comes out to be the lightest in weight really depends on exactly how the weight per unit area of thermal protection system scales with the heating rate. And that's a difficult question to which I don't have an answer. To first order, it tends to be a push. But there are some differences that more detailed analysis presumably is going to drive out sometime before too long. Ground operations, you can call that one either way. It kind of depends on your biases. The vertical lander obviously doesn't need a runway. That's an advantage. A runway is pretty big. The horizontal lander needs a runway that is pretty much like the runway at a large international airport, 10,000-foot runway. It's probably built in the size of the current SSTOs that we're thinking of, with 20 to 40,000 pounds of orbit. It probably does not need the 15,000-foot runway that the shuttle has. And the reason is that if you're going to bring back the hydrogen tank, which the shuttle doesn't do, then the platform area and the wing area for decent proportions of a vehicle like that are enough bigger than the shuttle, while the inert weight doesn't go up very much, that the landing speed is going to be significantly less, and therefore you probably land on a standard airport runway. Taking off from a standard airport is a much more difficult issue, because whether this is a vertical lander or a horizontal lander, if you want to take off with this vehicle, you need at least some kind of a launch stand, which may not be a big deal, but you also need a lot of hydrogen and oxygen propellant. And trucking a lot of hydrogen propellant into an international commercial airport is probably an issue. At least they're currently not set up for that sort of thing. So yeah, you can land the vertical one anywhere. You can land the horizontal one more or less anywhere, at least at any airport. But taking off again is a substantial issue for either system. The horizontal lander can be towed around on its wheels. The vertical one can't because it doesn't have wheels, but you can put a transporter under it and move it around. But the problem of the transporter for the vertical lander is roughly balanced by the problem of having a tilt-up erector for the horizontal lander. It lands horizontal, but when you want to launch it, you got to stand it on its tail. One issue with many of these concepts is that it turns out to be convenient for the vehicle designers in many cases to put the payload bay transverse in the vehicle. That is, the vehicle sitting here like this, whether it's vertical or horizontal lander, and if you put in a 15 by 30 foot payload bay, since the vehicles tend to be about 30 feet in diameter anyway, very horizontal, very tempting to put the payload bay in this way. There's two problems with that in my view. One is that many of your launch customers don't like that. They're really designed their payloads to be launched with the payload bay in the other orientation, like a Titan or a shuttle or whatever. And the second thing is, if you ever wanted to use this vehicle for tourists, they'd probably like to be able to see out. And that means you really ought to have a payload bay in which you can put windows. And the transverse one doesn't work that way very well. Reliability slightly favors the horizontal simply because you don't have as many engine starts to go through. And engine starts are a big deal when you calculate reliability. Aboard, there are a couple of differences. The vertical takeoff machine can indeed go into a hover mode and burn off its propellant and set down anywhere. The horizontal vehicle can't do that. However, it can go into a hover mode, burn off most of the propellant, and then climb to about 20,000 feet and circle around and do a landing approach to a runway. So both of them have the ability to do some sort of subsonic abort directly off the pad. The opportunity to do that like that doesn't last very long. Once you're about 30 or 40 seconds into flight, you're up to enough speed and far enough downrange that you're really going to have to do something like the shuttle return to launch site maneuver with either one of these vehicles. The other options for abort are downrange landing, abort to orbit, or abort to once around, which is almost an orbit, except you don't really quite get to a high enough orbital altitude to stay up and you come down after one revolution. One of the things, by the way, that caused the shuttle to end up with wings, and there were some versions of the shuttle that had that either had wings that didn't allow you to get cross range, or they didn't have wings at all. There was actually a vertical takeoff, vertical landing proposal in the early shuttle days. And some of us remember the infamous Max Faget straight wing orbiter, which actually entered at a 90-degree angle of attack, and it had straight wings like a subsonic airplane. And it had essentially no cross range capability. But one of the things that drove the shuttle to cross range was that the Air Force in the early days of the shuttle program had a mission that they wanted to fly, which amounted to a once-around flight out of Vandenberg Air Force Base. Now, as soon as you get into orbit, you're in inertial space, and the Earth is rotating under you at its normal rotation rate of 15 degrees per hour. So once you've come around after an hour and a half in orbit, Vandenberg has rotated about 22 degrees to the east, and where you come in is over the Pacific Ocean. Now, if you're not a water lander, you need to be able to make that turn about 1,100 nautical miles to the east in order to get back to land where you can land the thing, and that's why the shuttle ended up at cross range. It's not clear that any of these vehicles need abort to once around. But if they do, and if you're going to fly at a significantly high inclination, or if you're going to fly out of Vandenberg, or if you're going to fly out of any location that has ocean to the west of you, then you need cross range. That's kind of an obscure trade. probably isn't going to swing an answer in this case, but it is a factor. Now, so far, I've been mainly talking about as if there are two answers or potential answers to this question. There's really four. You can take off either vertical or horizontal. You can land either vertical or horizontal. And you can combine those in any combination, which gives you four combinations altogether. Now, to the best of my knowledge, no one has ever found a reason to want to take off horizontal and land vertical. So there really are three that we ought to think about, not four. And so far I've talked about the current RLV candidates, which are vertical takeoff, vertical landing, vertical takeoff, and horizontal landing. I did show some pictures of another option, which is horizontal takeoff. Now, a cynic would say, and some have, that there's always some idiot that wants to make a rocket take off horizontal, which is not natural, and there's always some idiot that wants to make an airplane land vertical, which is not natural. And one can find some examples of airplanes that land vertically, and so far I know of no cases of rockets that take off horizontally, and certainly not orbital rockets. But there have been many studies. The horizontal takeoff rocket has two really terrible problems if you want to take off from a runway like an airplane. One is that it's very heavy when it takes off. If you take the current RLV thing, the 20,000 to 40,000 pounds in orbit class, you're really looking at more or less 2 million pounds of takeoff weight, which is about a little over twice the heaviest 747 takeoff weight that's possible. You would probably, because of the inert weight problem of being able to get to orbit with one of these things, you would probably like to have your wing sized approximately for the landing and not for takeoff. And if you want to take off with that wing at 10 times the landing weight, that means your takeoff speed is probably going to be about 400 miles an hour. And you cannot do that from a 10,000-foot runway, especially not if you want to refuse takeoff capability like an airplane. The other thing is that the landing gear or takeoff gear of an airplane tends to weigh, well, it used to be 5%, now they've improved a little, it's 3 to 4% of the weight that's supported by the gear. Now, in the case of the landing of one of these vehicles empty, then that is 3 or 4% of the inert weight plus payload if you have to land with payload. But in the case of takeoff with all that propellant on board, then the landing gear, if it can support the propellant, tends to be 30 to 40% of the inert weight that's allowable. And nobody's figured out how to get to orbit with that penalty. So that's one problem. Well, the wings are one problem, and the heavy gear is the second problem. So engineers who have dealt with this problem, all the way back to Sanger, by the way, in 1942, have said that if you want to take off one of these things horizontally, you're going to take it off with some kind of a ground assist device. It's a takeoff dolly that you drop. It's a sled of some sort, say a steel rail slipper device sled. It's some other kind of sled. Maybe it's in the modern world. It's a magnetic levitation takeoff device, so that your landing gear on the airplane are folded and tucked away, just like the shuttle. When you take off, the vehicle is supported by this takeoff device, and also because you have now built this special facility for takeoff, you can accelerate to 400 miles an hour and take off, and you can have this thing have a long enough track that you have a refused takeoff capability. You can actually stop in the event you decide not to take off. Well, if you could do that, and that's not, we're talking about special ground facilities and some other things that cost money. But if you could do that, the first thing you'd find out is that I don't need as many engines. And I first looked at that problem 20 years ago. It was somebody else's proposal, not even a Boeing person. And he had this scheme for horizontal takeoff, and he had a thrust-weighted takeoff of about 0.7. I looked at that and said, that can't possibly work. That trajectory it isn't going to work. But we rounded up one of our trajectory experts and started running the computer. And after a while, we got a pretty decent trajectory. Answer, sure enough, it works. You know, you can actually take off and climb out like an airplane, and you get to orbit with about the same total delta V as you would for vertical takeoff. The difference is that about half your losses are drag, whereas in vertical takeoff, only about 10% of the losses are drag, and most of it's gravity. So I can take engines off of this thing. Now, one thing that's been learned in the commercial airplane business over many, many years is that the optimum number of engines for an airplane is 2. If you only have 1 and it quits, then you're stuck with a nearly immediate landing. But if you've got 2, and I recently read an article in which somebody said 2-engine airplanes are less reliable than 1-engine airplanes, but he was assuming that if you had 1-engine failure, you were going to crash. And in fact, airplanes are designed so that if 1 engine fails, you can land safely on the other one. In fact, you can fly sideways on the other one. The same thing would be true for rocket. The reason is cost. Engines are expensive to operate, whether they're airplane engines or rocket engines or whatever. The same answer would be true for rocket vehicles if you could handle the case of an engine failing. Now, if you take off vertically at a thrust to weight of about 1.25 is pretty typical, 1.3, somewhere in there, and you only have 2 engines and one of them fails, you're left with a thrust to weight of about 6/10 or 7/10, you're going to fall back and have a pad explosion. So you typically end up putting 4, 5, 6, or even 8 engines on a vertical takeoff machine, so that 1 engine fails, you've still got enough thrust to fly out. If you take off on wing lift with a horizontal takeoff rocket, you can take off with a thrust to weight of 0.8 or 0.7, and you can fly it on the wings with a thrust to weight as low as 0.3 or 0.35. So you could have a 2-engine airplane. And that has a significant benefit on the cost of operating the vehicle, because engine cost is a big deal. One might think that taking engines off gives me a weight advantage. In fact, it may give a little bit of a weight advantage, but most of the weight you get rid of by taking engines off, you have to add into wing weight, because you now have a wing which, although not a lot bigger, is a wing that has to support the weight of the airplane fuel rather than the weight of the airplane engine. And it's not, even there, the trade is not as dramatic as one would think. You think, here, I've got a 10-to-1 swing here. I really don't, because even with the vertical takeoff vehicle, the wing has to be able to sustain lifting loads on the order of 1 to 1.5 Gs just to survive flying through max Q and the wind shears and all that good stuff. If you take off horizontal, the wing probably has to be designed to handle about 3.5 Gs. And so the wing structure goes up by about a factor of 2. Most of the weight you save taking off engines you add back by putting on stronger and slightly bigger wings. But if you look at the cost number, it turns out that wing structure is a lot cheaper than engines per pound. It's cheaper to buy in the first place and cheaper to operate. But you do need a launch assist, and that's a major issue. And the current activities are not actually looking at horizontal takeoff. So while I like it, I think if I did have a magic envelope here with the right answer, it probably wouldn't be that, because nobody's looking at it very seriously right now. So what's the bottom line of all of this? And the bottom line, and although I'm not going to tell you it's vertical or horizontal or what it is, because I actually don't know, the bottom line is that, first of all, beauty is in the eye of the beholder. There are strong advocates for horizontal landing. There are strong advocates for vertical landing. There are people like me who are advocates of horizontal takeoff. The issue is difficult. The decision for a real RLV, assuming that the reusable launch vehicle single station orbit is going to be funded by private capital, that decision is going to be made by the people who put up the money. It's the old golden rule. Them says the gold makes the rules. It isn't going to be decided by me. It's not going to be decided by people in this audience in general. It's going to be decided by somebody who has to pony up the several $1 billion to do the research and development of this thing. It will probably be some combination of one or more corporate boards of directors and perhaps some outside financial interests, depending on how the thing is actually financed. Now, there's another very difficult issue facing the current X-33 people, and that is, and this issue goes beyond vertical versus horizontal. But the problem is that voters decided about X-33 has to be right. Because the X-33 is going to be the thing that convinces the investors that this is an investor with a risk, that this is an investment with a risk that they can tolerate. So we're not going to have the opportunity to fly an X-33 and say, well, we learned from that how we ought to have done it, but it wasn't right, but now we know how to do it. Because without a successful demonstration, I don't believe there's going to be an investment from the private capital community into an RLV. And so the problem is you got to make the decision on how you're going to build and fly an X-33 before you can fly and build an X-33. It's an age-old problem that's been around for years and years and years. We've got some partial demonstrations. The DCX has taken off vertically and landed vertically several times. We know that works. The shuttle has taken off vertically and landed horizontally, I think approximately 70 times. I don't know what the next STS number is, but it's around 71 or 72. From the standpoint of can you land it either way, the answer is yes. The real issues are in these other things that I talked about, and the question is difficult, and at least to me at this point, the answer is a little murky. I think we have about 15 minutes that I can field questions. Yes.
Considering when you were talking about the transverse cargo problem, what would be the situation if you had a vertical takeoff and a horizontal landing and had to abort?
I didn't hear the last part of the
Well,
question.
if you had a vehicle that was vertical takeoff, horizontal landing, and it had to abort,
You mean abort to landing with the payload in?
yes.
Then you have the same problem that the shuttle has, because that's exactly the situation with the shuttle. And the answer is the payload has to be designed so that in the case of a horizontal landing, even a horizontal crash landing, any scenario in which the crew could survive, the payload has to be designed so that the payload will not break loose in the payload bay and cause damage to the vehicle, which would kill the crew. Now, the answer for an RLV is probably a little bit less severe than that, because the RLV will probably not fly with a crew on board when it's carrying payloads to orbit. And so it's really kind of up to the payload guy. Do you want to be able, the vehicle owners are going to say, under a safe horizontal landing, when I can reuse the vehicle or even salvage it, I don't want your payload to break up so badly that it ruins my vehicle and wipes out my expensive asset. But except for that, it's up to the payload guy whether he wants to design to survive that anomalous condition or not. If this vehicle is as reliable as it has to be to make it work economically, the payload guy is going to take his chances. He's going to say, yeah, I'll design it so it doesn't break, but I'll take my chances on your report because that's about, one chance out of 100, and I got insurance that covers that.
I just wanted to give clarification. I worked with Lowell about the 80s, early 90s. The concept for DCX sort of had a mutual, more bigger involvement. It started back in the early 80s with a guy, Joe Shirty, and Art Robinson, who worked in the Apollo program. And they were real fans of something called Rhombus, which was the McDonald's equivalent.
That was Phil Bonos.
Yeah, Phil Bonos.
Yeah.
And so that kind of, we used that for a device called toss-back booster, which is a two-stage vertical takeoff, vertical landing device like Rhombus and Big Onion. We use that for the trans-atmospheric vehicle studies. And so there's a lot of crosstalk between the NAS people in St. Louis and and that's sort of where the DCX concept came from.
Okay, there also was, I didn't mention it, but there was also a concept that came out of Germany in about 1971 called Beta, which was contemporary with Rhombus. It was developed by Dietrich Kurla, and it was a little bit smaller than the current RLVs. I believe Beta had a payload of about 10,000 pounds. But it was a vertical takeoff, vertical lander, tail first entry. Thank you for the clarification. I remember the Rhombus, but I was not aware of some of the other ones.
For a launch vehicle that comes back vertically, is there a big range where we're coming in nose first, slowing down, the motion to land, or am I back in tail first and going all the way tail
That's a question I can't answer. I can tell you what some of the issues are, but I'm not involved in the current studies and don't actually know the answer to that. The tail first entry, from the standpoint of the guy who has to design the flight control on the entry and all that, is simpler to do because you don't have to worry about this turnaround maneuver. On the other hand, you do have to worry about protecting the engines from entry heating, which was kind of a thing that people in the old days of the big onion and so forth tended to overlook. They kind of said, well, we'll find a way to do that. We, in most cases, haven't done that. There's two schools of thought on how to do that, and one is to flow a little bit of hydrogen through the engine to keep, or something to keep the hot air out of the bell, and the other one is to have some doors that cover it. Neither one is a particularly comfortable answer. On the other hand, with nose first entry, you do have to do the turnaround maneuver, and there are two schools of thought on that. You either start engines before turnaround and you actually fly it through the turnaround, or you do an aerodynamic turnaround and start engines afterwards. So, you know, it's a good question. I don't have a good answer for you. Sure.
Well, quick follow-up then. If one was using a very high temperature ceramic nozzle, didn't heat up very little, then that issue would be partially addressed at least.
That would help.
Could you talk a little briefly about the system grades for aerospike versus extendable nozzles for altitude compensation?
I can give you my curmudgeonly, highly biased opinion, which is that aerospikes have been around for a long time, and when you really look at delta V to orbit, they don't help very much. Now, back in the days of low pressure engines, like the J2 engine with a chamber pressure of 700 psi and so forth, aerospike was a pretty good idea because the engine really, you could not put a big area ratio on the engine at sea level because the nozzle would not flow full. The J2 had an area ratio of 27, and in order to run that engine at sea level, you had to put a kind of a collar on it which recompressed the flow a little bit in order to keep the engine from separating at sea level. And the other thing they had to do in order to run the J2 at sea level on the S2 stage when they were test firing is that as the engine started up, the flow developing in the nozzle was, what happens if the nozzle separates is the flow does not separate symmetrically. It doesn't go off one side or the other side and generate huge side thrust loads. So the J2 for ground static test had not only these collars on the engine, it also had some bracing to hold the engine straight so that the side loads wouldn't damage the engine installation. The space shuttle engine at 3,000 psi chamber pressure has an area ratio of about 75. That's not exactly right, but that's close. And it has a big enough area ratio to give you pretty close to the vacuum ISP you want. The issue is not, you know, we used to argue a lot about altitude compensation, and the issue is not really altitude compensation because the effective delta V that you gain through good altitude compensation is only a couple hundred meters per second. It's not a big first order swinger. The real issue is being able to fly a high enough area ratio in order to get the ISP during the vacuum part of the flight that really gives you the performance. Two-position nozzle can do that. There's a lot of argument about whether two-position nozzles are worth the trouble. Some people claim the aerospike engine is lighter in weight. It does not have a big physical nozzle, but most of the weight ends up to be a combustion chamber anyway. My personal view is that I'm not a big fan of aerospikes. I'm a big fan, personally, if it was my money, of finding a way to do this thing with the SSME the way it presently sits, because a new engine is another $3 billion, and we've got a big financing problem with this thing. You know, a new engine is going to add 30 or 40% to the R&D cost of an RLV. Yes. Yeah, go ahead.
There was a period of time when people were thinking of using a slanted or curved launch platform for, to accelerate up. What was the reasons why they wanted to do it, and why did they decide against it, if you know?
Well, you know, again, that idea goes all the way back to Sanger. I think Sanger did not go up the side of a mountain in 1942, but I don't recall. I've not actually seen these papers or any drawings.
This was in when worlds collide.
Yeah, in Worlds Collide, they went up a mountain, and has been regenerated or has come back again recently in this maglifter concept. An early version of the maglifter, and I'm not sure what the current version is. The early version of the maglifter, which is a magnetic accelerator actually had a huge tunnel bored up through a mountain, came out the side of a mountain at a 45-degree path angle, and used a magnetic accelerator up to about Mach 6/10 or 7/10, at which time you came out of this tunnel in the mountain and the vehicle was launched. If you did it refuse takeoff, the tunnel actually did this kind of a number, and somehow I wasn't real convinced of that. But the point is that that scheme of going up the side of a mountain into a typical rocket flight path angle at 45 degrees or more loses the main advantage of horizontal takeoff, which is I don't need very much thrust and I can take a bunch of engines off. So you really want to take off at horizontal or at no more than about 20 degrees path angle upwards. I believe the current version of Maglector, which I'll probably get a look at tomorrow in Denver, does go up the side of a mountain at a relatively gentle slope, and that may be a pretty good answer.
Whatever happened to the National Aerospace plane and the idea of sort of combination jet rocket engines into space?
As far as I know, that program is essentially dead. The technical details on that program tended to be classified. I did not, part of the time, I don't currently carry a clearance because I work entirely in civil space, and even when I had one, I didn't have a need to know. So what actually went on in the program, I don't know. I produced a paper for the 1985 or 86, for the 1986 conference in Seattle, which was called Lower Bounds on Launch Cost, but in part it went into all of the reasons why getting to orbit on air breathers is pretty tough. And without going into configurations and all that part, it just dealt with physics. And at that time, I was pretty skeptical that you could ever build a device like that that actually gets to orbit single stage. And I still am. The problem is that air breathers have a crummy thrust to weight ratio. Even a subsonic jet engine with a high bypass fan, like you would have installed on, say, a 777 or so, installed has a thrust to weight ratio of about 5, perhaps a little less. Dana, you might correct me on that if I'm way off.
Sounds good.
A rocket engine has a thrust to weight ratio of about 60 or 70. Some kerosene engines over 100. The problem is that to build an air breather engine that also can generate thrust way through the supersonic range up into as far as the hypersonic as you can get, you end up with a big heavy installation, a lot of inert weight. And my estimate in 1986, and I haven't done any work since then, so I haven't changed it, is that the real Mach number you can get to with an air breather is probably about half orbital velocity, which says the second half you got to get with rocket propulsion. And when you run that trade, the problem is that the inert weight of the air breather hurts you more than the low fuel consumption helps. And so in 1986, I was skeptical of the air breather as a solution to this, and I still am. But it's as far as what actually caused the NASA program to decline and fall, I don't know, because the technical details of that program are always classified. You had a question?
We're going to have to make this the last question.
All right, fine.
Cut close.
Okay.
For the problem of the horizontal takeoff, fully fueled craft, and the problem of the landing gear,
Yes.
40% of the structural weight. Does that black horse concept kind of bypass that by having fuel halfway up?
Yeah, that's the idea. By putting on most of the fuel after you take off, you get around that problem. That's another solution. I've not looked into Black Horse in any detail at all. One of the versions used hydrogen peroxide. I think the Germans learned during the Second World War that wasn't a great idea. The ME-163, 163, is that right? I forget. There was a rocket airplane. It was the ME-163. They used to blow up occasionally for no apparent reason. And hydrogen peroxide is nasty stuff to deal with. I mean, just sitting on the ground, they'd sit there and boom. I think that Black Horse would be much better advised to transfer locks, which I think is probably not particularly difficult. It's not been done, but locks, other than the fact that you have to be scrupulously clean when you do liquid oxygen, it's not hard to handle. And by the way, hydrogen peroxide is even worse as far as being scrupulously clean. But it does solve the problem. Now, one of the difficulties, in my view, with the concepts that I've read about is they use a LOX kerosene class of system. So you have to have phenomenally low inert weight in order to get to orbit because you lose 100 seconds of ISP by going to LOX kerosene.